Welcome back. So as said, we want to talk about now an alternative for hard decision-based classifiers, namely probabilistic classifiers. So more technically, we want to model the distribution of the class label y given the data x. Okay? And as you all know, we can reformulate this based on Bayes' rule also in an alternative way, where we, for example, model the distribution of x conditioned on y times p of y divided by the evidence. Okay? So why did I show you this reformulation one more time? Because this more or less motivates two different views on this process of probabilistic classification. On one hand, we have the generative models, where we indeed model the joint distribution p of x, y, and we often do this in a very specific form where we factorize the distribution in p of x conditioned on y and then p of y, as we see it here on the right hand side. These are generative models, and we start with this topic, and you will see later why these are also called generative models. And then there are also the discriminative models, where we directly model the left-hand side of this distribution, where we directly model p of y conditioned on x. Okay? So these are the two approaches, but what you see is that in both cases, at the end of the day, we can find this distribution p of y, p of the label conditioned on the input data. Here, by reformulating it via Bayes' rule, here we get it directly. And then, of course, you know how do we get the actual prediction? We just look at the argmax again. We look at the class which maximizes this corresponding probability. So the most likely label, the most likely class for this data instance, x. Okay, so let's start with this generative model point of view. So probabilistic generative models for specifically linear classification, but we also see some extension for nonlinear decision boundaries. Okay, so again, so what do we need to do this? What do we need to find like a distribution over the class labels, right? So the most likely labels, we have to apply Bayes' rule, and then we see these two terms, which are in the classification setting are often called the class conditional, which is the distribution of, let's assume we know the class, right? So these, for example, these images are cats, then we model how cat images looks like, right? So this is like, it's labeled as cat, and here we have a distribution over the images, which are all cats because it's conditioned on the cat's image. Or similarly, if we know that this is a dog, right? These images are dogs, then we model the distribution over the images which contain dogs, so to say. Okay, so here we're really modeling the distribution over the data instances, so let's say the images, right, conditioned on the known class. And then, of course, based on Bayes' rule, we also need this class prior, which models how likely is a class at all. So how likely is it to see a dog, a cat, or a human, right? And again, here it's the distribution over the data. So we have the class prior and the class conditionals. And as it turns out, these are the two only points we have to specify to set up a probabilistic generative model for classification. The class prior and the class conditional, because then we can just, again, reformulate it and we get our final prediction for the class. Okay, so how does it look in more detail? Again, why is it also called now a generative model? So first of all, this is what I just said here, right? We have to pick these two distributions. We have to pick the class conditional, which has some parameters. We see later on specific instantiations. And we have to choose the class prior distribution, which also has some kind of parameters. And we also see that. So this is what we have to pick. And then, of course, what we have to do is we have to learn this. As we have also seen for a linear regression already, right? We picked, so to say, our model, right? So this is setting up the model, parametric model. So we have some parameters in these models which we can control. And then comes the learning step, meaning learning these best good parameters. And since we have here a probabilistic model, of course, one solution would be to derive a maximum likelihood estimate for these two parameters of these two distributions, phi and theta. Okay. And what I also said already in the regression lecture, this part is called learning. Okay, so once we have set up our model, our parametric model because we have here these parameters, then the learning step is indeed finding these parameters, which well explain the data, which are, for example, maximum likelihood estimates. Okay, so this is step one. And then once we have fitted our model, once we have done the learning, we can do the inference step. And again, what is the inference? Inference means we want to make, say, decisions, conclusions for new instances. In this case, because we're talking about classification, we get a new input X, which could again be an image. And then we want to make our prediction. We want to do the inference. So inferring, so to say, this distribution here, which gives you the information about the class label for this image, for example. Again, you see here the two terms we have set up before. Now we have here the learned parameters. Okay, so we are done with the learning. And then we can just do the inference, finding the prediction for a new instance. Okay, so that's a general setup we have to follow. And it's similar to linear regression as we have seen. Training, learning, and then inference, making the prediction. Okay, so why is this process called a generative model? It's called a generative model or a generative classifier because we can indeed use this approach to generate data from our model, generate input data, images, for example. Why? Because what we can do is now the following. First of all, we have our class prior. This is a distribution over Y. Okay, as we see in the next slide, it's usually categorical distribution because we have categories, right? Cats, dogs, and humans. And of course, we can, assuming we have learned this distribution or we have given this distribution, of course, we can randomly sample labels from this distribution, right? Think about, again, you have like 6 classes, right? Cats, dogs, humans, and so on and so forth. Then it's like rolling a dice, right? And whatever this number shows you on the dice, this will be a new outcome. This is a new label, okay? And once we have this label, we can do the same for our actual data X, for our images, for example, right? Because this here is a distribution over X over the data space, right? And once we have already decided on our class label, and we have already learned these parameters, then of course we can also sample from this distribution, okay? So a simple case would be that this here, for example, is a one-dimensional Gaussian, right? Let's say it has some specific mu and some specific covariance structure, right? So this distribution here, it's a multivariate Gaussian, for example. Then you can just randomly draw from this Gaussian, right? In a one-dimensional case, it means we're more likely here around the mean, less likely in the tails. But you can just think about this as a data generator. And this in general, what I recommend to think about this process, really think about it as like a data generator, as a simulation model, so to say. Once we have these two distributions, we have this two-stage process. First, we simulate, we generate a new class, right, from the first distribution. And then once we have this, we can also simulate in a second step to get a data point. And this is indeed what you could easily implement in any of these programming languages nowadays, like in NumPy, for example. You have also support for probability distributions. And you can just write down, for example, give me a random outcome from a categorical distribution. So give me a random class label, so to say, based on specific parameters. And then you could also say, give me a random number from a Gaussian, giving specific parameters, of course, again. And this will then give you a new X. Okay. And this is why it's called generative classifier, generative model, because you can really use it to generate data instances, images, so to say. So one more time, the probabilistic graphical model for this. So what we have seen is here, we have here this Y. Okay, so Y is our class label. And then this Y affects the X. Okay. So we see that first we have the Y, which only depends on some deterministic parameters theta, right? And then giving this Y here, right? So we have to pick the Y, then the Y together with these psi parameters here, right? They together affect or generate, are responsible for generating the X, okay? So of course, since we're here in a supervised learning scenario, these here are observed. So if you watched the video on Introduction to Probabilistic Graphical Models, you have seen that we are shading here the observed variables. And in a supervised learning setting, of course, the Y as well as the X are observed data, so they are shaded. And yeah, so this is what we can illustrate here. So again, this is usually very easy to remember, have this mental view, so to say, of this illustration. So we have the process as first generating the y, and then giving the y and our parameters, we can also generate the x. Okay, so that's the first view. So what we have to do now is to set up this model, right? We have to choose our distributions, how the x and the y, how they look like, so to say. And let's start with the class prior, with this distribution p of y, right? So the prior information, the prior knowledge about this y's. And since the y's are classes, right, we have discrete set of outcomes. More or less the only choice we can pick here is a categorical distribution. Okay, so categorical distribution, illustratively speaking, is like these different histograms, right? We have here 4 classes, for example. Every class has a specific probability to occur, and it sums up to 1. Okay, so this is encoded by this phi vector. So this is more or less like the only choice for this categorical data. And if you have a binary classification problem, 2 classes, then of course it boils down to a Bernoulli distribution, like this coin flip, 0 or 1. Okay, so that's the choice, and then the parameter we have to learn later on is of course this theta, which is the probability of each class. So as a side mark, and I already said this in the some other videos, so often we are representing this categorical distribution simply in some kind of an indicator view, because it's very compact to write. So remember, right, the distribution, so the probability that the class label y corresponds to a specific class c is encoded by this theta c, right? So this is a vector, and every element of this vector gives a probability for this class here, the histogram. Okay, so here 4 numbers. So instead of having this like case distinction, in class 1 I'm using theta 1, class 2 I'm using theta 2, and so on and so forth, we can just write it here as this kind of product. So you see that we here have the product over all classes, here we have the corresponding probability for this class, and here we have this indicator notation, which tells me if the y equals to class c, then this is 1, otherwise it's 0. Right? So you see that in every case, if this is let's say class 1, only theta 1 kicks in, because theta 1 to the power of 1, and all the other thetas, theta 2, theta 3, and so on and so forth, they are to the power of 0 in that case, so they disappear, so to say. So this indeed is a very compact form to write a categorical distribution without a case distinction, by just having here this indicator which tells you whether we use this part here or not, so to say. Okay, so this is our distribution we are picking here, categorical distribution. And indeed we don't really have to talk about this too long. So if we want to learn this parameter, let's say we want to do the maximum likelihood estimate, so the parameter which best explains our observed data, you already know the answer, because we did this for the coin flip, and you can imagine how to generalize this to the to k classes, not just 2 classes. Indeed, the maximum likelihood estimate for this parameter will just be the relative proportions, the ratios. So if we have 3 times class blue and 5 times class red and I don't know, 2 times class green, then of course the maximum likelihood estimate is just these ratios. So we have here 5, 6, 7, 8, 10. So it's 3 divided by 10, 5 divided by 10, or 2 divided by 10. So this is just the maximum likelihood estimate for this parameter theta, as we have seen already for the coin flip examples. So why is it here so easy? Because the y is already observed, right? So the way y is known in a supervised learning setting. So indeed, we can just really treat it as like doing some coin flip, right? So because this is given, we just want to know how do we have to pick this. Okay, good. So this was easy, right? So this class prior, categorical, sure, maximum likelihood estimate, also for free more or less. So the more exciting question is, how do we pick the class conditional? So how do we decide on how does this really this generative part looks like? So once we know the class, how should the data be generated, so to say? Okay. And again, so let's say we're in the setting that x is some d-dimensional vector. So again, you can think about like an image. So we have the image pixel values like in a matrix. We flatten it to a long vector, and then we have here our x as the input data, so to say. Okay. So what can we do? We can, for example, use a multivariate Gaussian. This is often a very good choice, right? Gaussians are nice to handle and capture nice behavior. So this is one idea. Okay, so we could say, for example, that this class conditional looks like a Gaussian asset, right? Where we have a specific mean. That's the mean for this specific class. And then let's say we have a global covariance matrix which describes, so to say, the correlation within this class. So how much is the spread and how is it tilted. So let's look at an example to make this a bit more clear. So here we see the setting. So let's say this is our training data. Okay, so we have here 3 classes given, class green, class orange, and class blue. And here we have 2-dimensional input data to 2 features, like 2 pixels, so to say, or 2 attributes of a person. Okay, and these are here the ground truth classes. Supervised learning setting, we have given these classes. So what this model tells you here is that on one hand, for every class, we have a separate mean. So we could say, for example, okay, here's the corresponding mean, mu1. Here's the other mean, mu2, and here's another mean, mu3. Right? So every class has its own mean. And then we have some global shared covariance matrix, meaning if we want to illustrate it here, like with these ISO lines, so to say, we have here like these Gaussians. Okay, we cover these, of course, again, multivariate Gaussians, right? They start here and they extend. I illustrate here just, so to say, the ISO lines of these Gaussians. Okay, but the covariance is the same for every of these classes. This is just one assumption we make, and I'll tell you in a second why. But here you see how these class conditionals look like and what they would capture, right? So you have these means and you have the Gaussians, and now you see that this indeed can be used to generate new data. Okay, one more time. So you first decide on a class. This is here like this step. You can randomly generate in NumPy or whatever famous language you want to use or library. You can randomly pick a class label. So let's say class blue. Then you know, okay, this is a Gaussian with this mean and a specific covariance. And then again, you can call your function and you get a random sample from this Gaussian, which could be, for example, located then here at this position. Okay. And then you repeat. You randomly sample another class label. Now let's say it's class orange, right? You know you are here. And then you take this mean and you take this covariance and you end up, for example, here. You repeat, right? You sample again a class label, so it could be class blue again. You know it's this mean, it's this covariance, and you sample, so for example, you are here. And then you see if you do this multiple times, you will get here back, hopefully, data which looks like your training data, right? If your training data follows these distributions, then you have here these nice 3 circles in this case, class blue, class green, and class orange. Okay? So this is how you can really look at this process. So one remark here. So some very important remark, and this often confuses people as well when you see this for the very first time. So we have now described really like a process how we can generate data. Decide on a label, decide on a color, so to say, and then randomly decide or randomly generate a point and repeat until you have these generated this bunch of data points. Of course, in practice, we do the inverse process, right? We do not want to generate data, but we have given data and then we want to infer the class labels. We want to learn the parameters, right? So again, like shown here. So of course, this process, which I just described, is a generative process. We can generate data. We can generate Y's and we can generate X's. But later on, we have the inverse direction, so to say. We have given this data. You see it's shaded here. And we want to first learn these parameters. And then we're going to use them for inference. Okay? So we do this inverse direction. So why still is this helpful? It's helpful because this generative process often gives you a very nice intuition how these classifiers in this case work, right? Because I guess we all agree that how we can generate data is very intuitive. Do the coin flip on the class label, do the randomly sample from a Gaussian, do another coin flip to get a class label, to get a color, so to say, and generate a point from the Gaussian, right? So this data generation perspective is very easy to understand. And then this learning and inference part is just some mathematical inverse problems, so to say, right? Where we can, where we derive these parameters based on the given data. Okay. Good, so this is our setting as set, right? So here we assume a very simple generative process that every data point follows this Gaussian. Again, another side remark here. Of course, in practice, the data might not perfectly follow this Gaussians, right? So if you have, let's say, images, for example, very high-dimensional images, it's very unlikely that they are perfectly coming from a Gaussian distribution. Still, this hopefully might be a valid assumption, and if this assumption holds to some degree, then we might get a nice classifier at the end of the day. But if the assumptions are completely violated, as you might expect, right, then the classification result at the end might also not be very good. It might not generalize, okay? So please be, so to say, careful what you pick here. Gaussian might be a good case, but don't expect that your data perfectly follows this kind of Gaussian. Good. So let me quickly talk about why did we pick this choice and what follows from this choice. So we said here we have one separate mean per class, but then we said we have a shared covariance matrix. So why did we do this? We did do this because if we would pick also a separate covariance matrix per class, we would have very many parameters, right? Remember that here, this here is also a d-dimensional vector. So like the input data, which comes from a d-dimensional space, of course, also the mean of a Gaussian is from this d-dimensional space, right? If you have a one-dimensional Gaussian, the outcome will also be one-dimensional. If you have a two-dimensional Gaussian, the outcome will also be two-dimensional, of course. But this matrix here, this here is a covariance matrix. It's a d times d matrix. And if you would have now even this individual per class, you would have very many parameters which you need to learn. Because you have number of classes parameters, and for every of these classes you have d plus d times d parameters. So in the order of d squared parameters, okay? So this is why in this case we assume it's a shared covariance matrix, and then the number of parameters we have to learn in this model is for every class C, we have to learn d parameters for the mean, and then we have this d times d parameters for one covariance matrix. Okay, so this is the number of parameters. Oops, this is the number of parameters we have to learn. C many means, but one covariance matrix only. Right, this is much more parameter efficient than having here also a separate covariance matrix for every class, because then it would be here times C even. Then you would have C times d squared parameters, which would be too much often, specifically if you have high dimensional data. And this is why we restrict ourselves to this shared covariance matrix. So as mentioned here, if you have lots of data, you can think about learning here a separate one. Lots of data per class, we should be specific here, right? Because per class you have a covariance matrix. So only in these cases you should do here also full covariance matrix per class. Okay, so this is our simple model. And now you see, similar to this prior, we have to learn, of course, this distribution, right? So we have to learn the mean and the sigma overall. So we will do this in more detail in the tutorial, or you can also look into the Bishop. Here just the high level intuition, not surprisingly what the outcome will be. So of course, if we look for the maximum likelihood estimate, the mean per class, assuming here Gaussian, is simply the empirical mean of all blue data points, so to say. Right? You have your training data, you take the ones which are labeled with class blue, right? And then you compute the empirical mean of these, and this gives you your mean. You take all the green labeled instances, so to say, all cat images, and you compute the mean of them, and then you get your mean. Okay. And then similar for the covariance matrix, it's only slightly different, right? Remember, in the covariance matrix, we usually scale the data with respect to the overall mean. So what we have to do now is every point is, so to say, normalized with respect to its own mean, right? We shift them with respect to their own mean, right? So they essentially become centered here, and these points also become centered here, right? Because for every point we are subtracting its own mean. So then we have all data points located here around this origin, and then for this we can just compute the covariance matrix, so to say. Okay, so that's the only difference, that we don't subtract from every point the global empirical mean, but we just subtract their individual mean, so to say. But other than that, we get the same calculation for the covariance matrix. But again, more details will be discussed later. It's rather straightforward though. And then more or less we are done, right? Now we have solved these two steps, right? We have picked our model family, here categorical, here multivariate Gaussian with a shared covariance matrix, and we know how to learn these parameters, right? So we are done with the learning step, and now we can apply this to new data. You can apply this to new data by just plugging in the values, right? So if we get a new data instance, right? So what do we have to do? We can, for example, I guess we have it in detail in a second. Yeah, we don't have it here in detail. So what can we do? And let me just explain it. So what we can do is we get a new instance, right? We get a new X, for example, and we can more or less now just enumerate all the different possibilities. Okay, so let's say we have two classes only. In this case, we discuss in a second in more detail. So we can first of all assume, okay, let's assume it's class 1. So what is the likelihood for this sample under class 1? Okay, let me just draw it actually. So let's say here you have a one-dimensional input data. Let's say you have learned a distribution for class red. Remember, for every class we have a specific distribution here, right? And let's say we have learned one distribution also for class blue, and let's say we have this 3 classes, even one distribution for class green. Okay, and now comes a new data instance. Let's say the data instance is located here, right? This is our new X, so here's the X domain. What we have to do is we have to just evaluate these terms based on the base rule, right? So meaning, first of all, okay, what is the likelihood of class 1? We look at the categorical distribution. The categorical distribution here might tell us, okay, our 5, for example, is like, I don't know, 30% class 1, 30% class 2, and 40% class 3. Okay, so let's say it's red, blue, and green. Right, then you would see, okay, for class 1, I have 30% here. And then I have to evaluate this term. So here it's class 1, and I have to look at this normal distribution, at the Gaussian, right? So I have to compute the density at this position, right? I pick the first Gaussian, the red Gaussian. I have my data instance X, and I see what is the density at this position. That's this term here, right? So how likely is X coming from this Gaussian? Okay. So I compute this term, which is here a rather high number. So I have this high number times 0.3. This is this term. And then I continue with class 2. Class 2 has also here 0.3, but with respect to class 2, this is a very low value, right? So if we continue here, these lines, you see the density of this X with respect to the blue class is very small. So it's very unlikely that this X comes from this blue curve. Okay, so here we would have a very low term. Okay, so it's 0.3 times a very low term. Okay, and then the same for the green here. Right, so here it's a very low likelihood that the X comes from the green curve. So it's 0.4 here times a very small value. And then you see, right, that the class 1 is winning, so to say, because class 1 had here 0.3 times a large value, right, because we had here this one, and this is then the winning class. Here we just have to normalize these classes, right? We get here 3 different numbers, so to say, right? The class 1 score, the class 2 score, and the class 3 score. We have to normalize it to make it a proper distribution, right? So sum it up and divide, so to say. And then you get the distribution. Then you take, of course, the largest one. Okay. So again, for the decision, for the inference, we really also have to just evaluate these two distributions. We have to evaluate how likely is it that it's class 1, for example, and then how likely is this X coming from class 1. Okay, and then we just test all these different cases, and we take the one with the highest solution here as well. Okay, so this is how we can make inference in such a model. Okay, just to wrap up one more time, We pick the model, we pick the distributions, we do the maximum likelihood estimate, we learn these parameters, which is rather easy in these cases, and finally we can do the inference by just checking what is the probability for every class, using again this Bayes rule, evaluating these two functions. Okay. By the way, in many cases, if we have like balanced data, meaning that every class has the same amount of training data, 100 images class dog, 100 images class cat, and so on and so forth, this term more or less just disappears, right? Because every class has the same fraction, so to say, like, I don't know, 10% of the data is for 10 classes, then this term just disappears, and then we can only evaluate this term, and then it's very efficient, of course. You just have to see, okay, is it more likely class red or more likely class green or more likely class blue? And you see it here, it's class red. Good. So this is our first model where we pick this specific class conditional structure. And this model is called LDA, Linear Discriminant Analysis. Don't confuse it with latent Dirichlet allocation, which is a model for text mining, for topic modeling. So this is also called LDA, but here we use the LDA, which is called Linear Discriminant Analysis. And now you might wonder, why is this called Linear Discriminant Analysis? And this is what we want to discuss in the following here. So what did we do here? And this is more or less what I just here actually described with this drawing before. Here I've shown you, so to say, the inference step, or how do we make the final prediction. So if we, for example, assume we have two classes, right? So what we have seen is to get the class 1 probability, we have to evaluate the prior at class 1. We have to evaluate the class conditional at class 1. Right? So this is what I just described on the previous slides with this small drawing. And then, of course, to make it a proper distribution, we have to normalize by these two terms. Okay, so here's the term for class 1 and here's the term for class 2. If we have more than two classes, you can imagine that we have here even more terms to normalize. And we just have to enumerate all these possible classes. Okay? So, of course, by the way, in a binary setting, it's enough to look at one of these classes, because the other class is just one minus of it, right? So here it's really sufficient to look at the probability of class 1. Okay? So this is what I just described from before. To make a prediction, we have to evaluate these two terms and we have to normalize, and that's it. Okay? So let's see how it looks like here. Let's reformulate it for a second. So these terms, we can use a specific shortcut. So let's introduce here this A term. And the A term is defined as the log ratio of these two different values, the two different let's call it likelihood terms or probabilities, right? Where we have always like the class 1 and class 2. Okay, so we have the ratio of class 1 divided by class 2, and we take the logarithm of this. Okay, which would be the same as log this minus log this, of course. So why is this shortcut helpful? Because then this term can be rewritten in such a way that it's 1 divided by 1 plus e to the power of minus a. So just please do this at home, plug in here the a, and then see how you get from here back to this solution. These are just some simple and standard rules to apply. Okay. So this is how we can write it using this notation of a. And why is this reformulation nice? Because this term here is a very famous function, at least in machine learning. This is a sigmoid function. Okay, so the sigma here, which we use as a shortcut, this is known as a sigmoid function. So 1 divided by 1 plus e to the power of minus the argument. Okay, so what we see is that the probability of class 1, or that the data sample x is labeled as class 1, this probability is simply like applying the sigmoid function to this term a, okay, to this log ratio term. Okay, so this is a, so to say, the model we are using to make our prediction, the sigmoid of this a term. So let's now look how this a term, so to say, looks like. Okay, so this a term, as we defined, right, it's here like this this log ratio. And now let's assume what we did before. We assumed before we have like per class a specific mean, mu1 and mu0 in this case, right? Mu1 and mu0 because we have two classes, but we have a shared covariance matrix. Okay, so we plug this in now. So here again, this was a Gaussian. this is what you see here. So this is our Gaussian term, so x minus the mu, and here's this the covariance matrix, or the inverse of it. And here we have our prior, class prior, and here the same for class 0, right? So from the denominator, that's the Gaussian term, that's here this term, and then we have our prior, okay? So this is simply plugging it in. And now we use, again, some other shortcuts. So we define a W equal to this term, right? So it's like the difference between the means and the covariance and the W0, this very long term. So why did we do this? Because if we use these shortcuts, we get this solution here, okay? So again, please, for yourself, plug in these two here and then see how you end up at this solution. So what is important to note is that these terms, they do not include x. Okay, so these terms are fully determined by mu's and sigmas, and that's all. Okay, so these here are independent of x, so these are constants, so to say. Once we have learned our parameters, once we're done with the learning, we can compute these. These are constants, right? Because they are now given, and then this here is the only part where x appears. Right here is the only x, and these are all constants. So why is this now helpful? And now we have to look back again here. So what is the prediction for class 1? Class 1 is the sigmoid of A, okay? And just as a drawing, right? So how does the sigmoid function looks like? Right, so if here's your domain, let me not call it x, let me just call it t, for example. And if we are drawing like the sigmoid function, and many cases I can't draw it, but here it's say 0.5, and here it's 0. So the sigmoid function goes up like this and like this. Might be steeper. As I said, I can't draw it usually. So it looks like this somehow, like an S curve. Okay, so it's flat here, then it's steeper, and then it goes like this. So the steepness can be controlled by stretching it or expanding it, right? But it's like this S-shaped curve. Okay, it's an S-shaped curve, which at the position 0 hits the 0.5, and it goes to 1 here. Actually add this, so here's 1, and here's the 0, of course. So it goes to 1 in the limit to the infinity, and it goes to 0 in the limit of minus infinity, and at position 0 it hits the 0.5 bar. Okay? So what does this mean for the probability? So the probability of class 1 equals to 0.5 if A equals to 0. Okay, so A equals to 0 means the probability for class 1 is 0.5. Okay? But differently speaking, if A is larger or equal to 0, we have larger or equal to 5. Okay? So meaning, if we want to predict it as class 1, which means the probability, of course, should be at least 0.5, at least 50%, because the class 0 has 1 minus of it. Right? So remember, P of y equal to 0 is, of course, 1 minus P of y equal to 1. Right? So if we want to make sure that the sample gets classified as class 1, we have to make sure, so to say, that A equals to 0. It's larger than 0, sorry. Right? So larger than 0 means it's class 1. Smaller than 0 means it's class 2, class 0. And this should remind you somehow already at what we discussed in this hard decision boundary case. Right? In the perceptron, for example. In the perceptron, we said if it's on one side of the hyperplane, then it's class 1. And we could compute this by checking whether the hyperplane evaluates to a positive term, larger than 0, class 1, above hyperplane. If it's below the hyperplane, what we have seen in perceptron is that the hyperplane evaluates to the negative value, so to say. And here it's similar, right? If A is negative, it becomes class 0. If A is positive, it becomes class 1. Okay? Good. And most importantly, of course, if A equals to 0, A equals to 0, exactly 0, then of course the probability is 0.5, meaning class 1 is 50% and class 0 has 50%, so for both classes have the same probability, so we are undecided, so to say, meaning this is the decision boundary. So A equals to 0 is exactly the decision boundary. So now you see some nice results, which I already said already a bit. So this here means decision boundary, so to say. Decision boundary. If this is equal to 0, then this is exactly the decision boundary. If this evaluates for specific x to 0, then x is on the decision boundary. But this is exactly what we have seen before, right? This was exactly also our definition of this linear hyperplane approach we had, right? We had the hyperplane, and once the hyperplane evaluates to 0, then this was our decision boundary between two classes. Put differently, what we have here is also just a hyperplane, right? This is a definition of a hyperplane, right? As before, this is, so to say, the normal vector, and here's the offset, the bias term, and the decision boundary is equal to 0. If it's positive, it's on one side, class 1. If it's on the other side, if it's negative, it's class 0. So we again see that this LDA approach, which we picked here, it's called LDA, it's called linear discriminant analysis, because we have a linear decision boundary at the end of the day. Okay? So here, it's again written what we have then, right? So because this can be written as this sigmoid of A, and this A, if we reformulate it in these terms of these W's, is really just sigmoid times here a linear function. Okay, so the only difference, so to say, or some of the only difference to the previous case was, there are two actually. On one end, we don't have a hard decision. It's not if this is positive, it's class 1, and if this is negative, it's class 0. But it's here also the sigmoid. And I said the sigmoid is some value between 0 and 1, right? It's this S-shaped function, so it gives you some value between 0 and 1, and not just 0 or 1. It's not a step function. Actually, let me draw it in the middle. It's not a step function, but it's like some continuous function between 0 and 1. It gives you somehow like a probability, right? It gives a probability and not just a hard decision. That's one core difference, right? And the second difference is that here in this LDA approach, these W's, they are actually not free parameters, right? You can't just pick them arbitrarily, but they have been derived based on this here, right? So please be careful in this LDA approach. W and W0, they have a specific structure. They just come from evaluating our probabilistic graphical model, right? Our probabilistic formulation. So W is this equation and W0 is the other one, okay? So how does it then work? So how can you now use an LDA approach in practice? So what you do again is, right, you assume your distributions, categorical and Gaussian. You compute your maximum likelihood estimate for the mu and for the sigma, or for multiple mu's, right? For every class you have a mu, and for the sigma, right? You have your estimate for these, right? You have the MLE estimates for these. You compute your W based on this closed form. You compute your W0 based on this closed form, okay? And now you have your W and your W0. And now if you get a new sample, right, a new data instance, an image, right, you just evaluate this term, right? So this is what you have. This is your new image. This is what you have. You evaluate this term, you plug it into the sigmoid function, and then you get the probability for class 1. So this is how you can use this model. Or put differently, what we just have defined here with the sigmoid is again just a Bernoulli distribution. Okay, the definition of a Bernoulli distribution, your Y, your class label, is distributed. It's binary classification. It's a coin flip, where this coin flip has not always the same probability, right? But the parameter, so to say, of the coin, right, of the Bernoulli distribution is our theta. But of course, it depends on X now, and of course, it depends also on W and W0. Okay, so you can think about this, that your class label is the outcome of a Bernoulli distribution. It's a sample from Bernoulli distribution, where the parameter of this Bernoulli distribution depends on the X, on the data you are getting at the moment, and based on your learned parameters, based on the equations we have seen so far. Okay? And here again, you see that we have a probabilistic model. that it's not just some arbitrary choice we have made here, but we have a probabilistic model how this process looks like, where we have now here the distribution over y. Here it's actually the posterior distribution, because we decided on a prior and we decided on the likelihood for x, and then we can derive the posterior with respect to y. Okay. So how does it look like graphically? This is what you see here in the lower part. So here's just an example. So here, I mean, the class prior distribution is not so interesting to show this, like this histogram, for example, the P of y distribution. Here we, on the left plot, we show the class conditional P of x, and you see we have it separate per class. Okay, so we have one distribution for class red. So here, this is the input space. So let's say this is x1 and this is x2. And here you see like the density, so to say, right? So here on the upper part, you see the density. So the density P of x for red and for blue. So this is what you see here for two-dimensional setting. So this essentially corresponds to what I have drawn here, but you have to imagine that the third dimension corresponds to the density. Okay. So this is what we see in this plot. And then here on the right-hand side, you see the final result for y, meaning what we are plotting here is indeed, here again, x1 and x2. And here on the axis, we are plotting the this P of y function, P of y equal to 1, condition on x, of course. And you see that if it's very close here to this +1, right? So here it's getting positive and here it's getting positive. Then it's unlikely in class 1, unlikely in class red, so likely in class blue. And if you're going to that side of your space, so if you're going to minus infinity, so to say -1, you see class red has a high probability. So be careful with these two plots, right? They really show two different things. So here we show the density of these different classes in the input space. So where do we expect the red objects and where do we expect the blue objects? So if you want to draw it, so essentially here we would have many blue objects and here we would have many red objects. If you think about the generative process, right? In the generative process, one more time, you have the red distribution, you have the blue distribution, you can generate samples, and here you end up the blue samples, here end up the red samples, right? So this is our P of x view, and here we plot the P of y view, which was our sigmoid function. You see here the S curve again. Right now you see the S curve in a two-dimensional space, right? So you have two inputs, here you had one input, and here you see how this S curve looks like in this space. Here it's class red, here it's class blue, so to say, unlikely class red. Okay. So this is LDA for two classes. In general, we might have multiple classes, right? We might have multiple classes. And let's look at this also quickly in a bit more detail. So more or less the theory is equivalent. It's exactly the same, and we already discussed this in this toy example. Because what do you have to do to evaluate the probability of the sample being labeled as class C? You just have to compute again the class, the prior and the class conditional for the specific class. And the only difference is here that you do not only have two classes, but you have arbitrary many classes, C classes, right? So for every class C prime, you have to evaluate this term and you have to normalize it, okay? So that's the only difference. And if you now plug in again your Gaussians and your categorical distribution and rewrite it a bit, then as it turns out, it boils down to this solution where we have here again some Wx and W0. We have this for every class, which are defined here in such a way. Okay, so here's the definition, and please again derive this yourself again. So there's one important difference here in the more than two classes case. As we discussed at the beginning of this classification lecture, for multiple classes, we often use this multi-class discriminant idea, meaning for every class we learn a separate function, this separate linear function, okay? So here we have C many functions. So if C equals to 3, we would have 3 different functions, for example, okay? So please be careful with this derivation, or here rather this one, where we had only one function, even though we had two classes. Okay, so what we indeed did here in this case is we already simplified it, that because we know that in the two class setting, one class is just the other, so one minus the other, right? So class 0 is just one minus class 1. So here actually we don't need two functions. It's sufficient to have one function, right? Because the other one results from this. Right, so let me actually just draw this. So if we have, for example, here class red and here class green, it was, of course, sufficient to have here like one hyperplane. But in the general case, in the multi-class discriminant case, we, for example, had, let's say, 3 ones, and then we have derived function for every class on its own, and then, of course, we might have three different functions we get. So here for every class we have its own linear function which we have to evaluate. Okay. So there are a couple of more points I have to explain now in more detail. So here, again back, here in this case, what we have seen here, that this function, we can set it to 0, and this equals already then to the decision boundary. So this here, this function is really like the separating hyperplane we are getting here. Okay, so this is the separating hyperplane corresponding to this one. What we are getting in the multi-class discriminant case, and this is not just now for LDA, but in general, when we learn these multi-class discriminant models, these are not directly this, the separating hyperplanes, right? These are not directly these functions. So how do we get these functions? And we quickly discussed this before, but let's say here this is class, let's say this is class 1 and this is class 2, right? And this is class 3. So what we know is that for every class, we are getting a specific hyperplane, right? So we have, for example, W1 X, so here's transposed in this notation, plus W1, the offset. And for this decision boundary, we know that it corresponds to one where both functions here, or both functions here, have the same value, right? This is what we said. In the multi-class discriminant case, it means we have here these individual functions per class, and where they agree, we have this undecided case, we have the decision boundary, okay? So indeed, these decision boundaries here in this case, they result from evaluating this term here. Okay, so here in this case, the function for class 1 and the function for class 2, they agree. We have this undecided decision. Okay, so this is what we have here for the left side and for the other class on the right side. And if we now reformulate this, right, if we reformulate this to put this on one side, of course we would have something like W1 minus W2 times X plus W1 0 minus W2 0 equals to 0. So as it turns out, this of course is now here again like a linear function, right? So this here is some constant, normal vector times X plus some offset equal to 0. So here this is again a linear decision boundary between these two classes, right? It's between these two classes. Okay. So again, please be careful that in these drawings, these lines, they only follow, they follow implicitly by solving this, putting all on one side. While here in this case, we already did this a priori because we know that one is the other one minus one, or one minus the other one. And then we immediately get here this solution. You see it also here, right? So here we have this one minus the other times the covariance term. Here we just have this covariance in one class, and you see it here then, right? So this here equals to this here. So the first one equals to this here, and then we have here the minus, and we take the other one out. So you indeed see that this is the same as before. This is, you can even write it. So this bracket would indeed boil down to something like covariance inverse times class 1 minus class 2, right? Which is exactly the same as we have seen here, class 1 minus the other class. Okay? So this is how we can derive the decision boundaries. Just be careful that here these terms are something different. They are per class. Okay? One other drawing which then is actually quite helpful here is the following. So what we actually derived in this plot is something like this. So let's say again we have here red. Let's say we only have two classes, blue. Here's our coordinate system. Let's assume for a moment that this is an identity matrix, so this disappears. So what we have is essentially that the normal vector, this is right, like the normal vector of this hyperplane we're computing corresponds to the mean. Okay, so put differently, if you have here your mean, you would have here your W1 and here your W0. W2, I guess. Right, so this is the mu, which is here, of course. So this would be W1. Here's the other mu, which would be the other vector. Okay. So these are these two vectors again. And they are the normal vectors of hyperplanes, right? So they are spanning up a hyperplane, which is like this here, which is 90-degree angle to this vector. And this guy is having here like a different, this is a different color. Has here this other hyperplane. Okay, so these are the normal vectors. Be careful with the offset, right? The offset might shift it somewhere else, but these are here like the two hyperplanes. And then again, however, what we have as a separating hyperplane is one minus the other, right? So what do we get if we have, for example, this this vector here minus this vector, so we have to walk along this direction, so to say we are getting something like this minus this here, right? We are getting some vector which, okay, now I have to, in this drawing, I have to make sure that the scale, it's a bit different in the scale, but I guess you all get the idea. So we have this vector and this vector, and I like to let's do this minus this one, I guess it's easier to draw. So we have this vector minus the blue vector, which goes here. So this would be like the difference vector. Roughly, it's not perfectly now in scale. It would be something like here, let's say. So the length does not fit now, right? So the length should be somewhere slightly different, right? But it's roughly like red vector minus the blue vector, right? So actually would be a bit more like this here. And then this would be like the difference vector. And then if we would draw then again a line and perpendicular to this, right? Orthogonal. So here it's orthogonal to it. We see that we get this separating hyperplane. Okay, one more time, what is important, you have here also this bias term. So this line here might be shifted up or down, so to say, right? So because I've here drawn this vector not in the correct scale, right? So you see red minus blue would be more like a vector going outside of my slide here. So the vector would point to this direction, then the black might look like this, for example, right? But since we have here also this bias term which shifts it to the origin, it might be shifted like here. But most importantly, the tilt of this hyperplane is such a way that it's separating these two classes. Okay, so this is what you should use as here as a takeaway. So this here is a bit like explaining every individual class, so to say. But of course, this here is the separation and it changes the tilt. So here the tilt is like this, here the tilt is like this. So if we take the difference, the tilt would be like this here. So it's separating red and blue. Okay. So this is what I quickly wanted to discuss. So the W's are these here. And then this hyperplane is, so separating hyperplane is like this here. Good. So then quickly back to this drawing, just to complete this picture. So indeed, what we are getting here for this picture are these kinds of separating hyperplanes. If you plug in the previous equations we have seen and solve it equal to 0, we see that we would separate here, and here, which is like always like cutting between these points here. Okay, and you see this is like a linear decision boundary. We have a linear separation between the classes. Good. So one last point I want to mention here on this slide, because that's a word you will often hear. So what we have here is the so-called softmax function. Okay, so the softmax function, you see it's defined here in the lower part. The softmax function is it's taking usually a vector as an input, and what it's doing is it takes every component of this vector, e to the power of this component, and it normalizes it by the sum of these elements. Okay, so it takes a vector as an input and it normalizes this and before taking the e of these terms. Okay, so this is softmax function. Let me talk about this quickly. So what is this softmax function doing? So you see, since we are normalizing here by the sum of all these terms, this outcome summed over all elements will always be equal to 1, right? So if we have here like sum over every component, this will always be 1. Okay, so this here will span indeed like span up like a probability distribution over the k-dimensional space if you have k input dimensions here. Okay, so let me do it in a bit more detail. So what I mean with this is, first note, of course, that this here would be, using this notation, would be a k-dimensional vector, right? So here we say the input to the sigmoid is k-dimensional, right? So this is a k-dimensional vector. In the previous slide, we used k equal to the number of classes, right? So k equals to the number of classes. And we feed in here a k-dimensional vector, we get out a k-dimensional vector. But important is that if we sum over every component of this k-dimensional vector, it sums up to 1. And it's all positive as well, because you have here e to the power of something, so the outcome will always be positive. So what is this then, actually, what this here returns? This is always a vector from the so-called probability simplex. Okay, so meaning it's a vector where all components are positive and where they sum up to 1. Or simply speaking, what you're getting out is something like a histogram, right? Where you have here k many classes, right? And all these components are positive because these are probabilities and they have to sum up to 1. Okay, so indeed this softmax function, which is applying this operation, transforms an arbitrary k-dimensional vector to a vector from this probability simplex. You can always interpret it as some probability distribution, a categorical probability distribution like this histogram. Okay, and of course, not surprisingly, if for a specific dimension here the value is large, right, also the output will be large. Okay, after this softmax transformation. Okay, so in the machine learning models, and specifically also in neural networks, you're often seeing here actually the softmax function to transform these vectors to some probability simplex to later on have some interpretation of probabilities that we can say, okay, class, what is it here? Class 4 has the highest probability of 0.6 and class 1 has this probability and so on and so forth. So here's just the formal definition as discussed, right? So it takes a k-dimensional vector, it maps it to the k minus, so denoted here with the simplex to the simplex. Please don't confuse this with the dimensionality. So the simplex is defined as a k-dimensional space where all components sum up to 1 and are larger than 0, but it's called the k minus 1 dimensional simplex because the last component is already completely determined. It's like if you know the first k minus 1, you know the last, right? Because it has to sum up to 1. Okay, so this is why it's k minus 1. But this is in general the definition, so it maps from the arbitrary k-dimensional domain to the domain of non-negative vectors which sum up to 1, which you can interpret as probabilities. So that's the softmax function you should be really aware of. And here we have used it indeed, as you see. So here we have like this e to the power of the solution for one class, and we divide by all the other classes. Okay. So how can we usually write this, or how do we usually write this in the softmax notation? So you can think about the following. So let's say we have here our softmax. So this is not the sigmoid anymore. This is the softmax, so the generalization of the sigmoids to multiple dimensions. And now instead of doing this here for every class individually, you can think about like having a matrix W. Let me just first write it down. You have a matrix W which has this size, what did we use? C or K times D, right? This, as before, was our d-dimensional vector, right? So let's make it specific, d times 1 then. And this is also a c-dimensional, or c times 1 dimensional vector. Okay, so what did I do here? So here you see that we have here this WC0. So for every class we have its own offset term. And here I've stacked all these together. Okay, so think about you have 3 classes, then every of these classes has this term, and here we have all these 3 values stacked together. Okay, and here I did the same. So here for every class we have a vector, so a d-dimensional vector, right? So this normal vector, which we have seen here, right? Every class has its own normal vector, WC. Here we have stacked next to each other all these different normal vectors, right? You see for every class C, I have this d-dimensional normal vector. Okay, so that's this matrix here, this stacked. For every class C, I have this normal vector. Of course, I can multiply this with the input data, which essentially means we are evaluating this term for all classes at the same time, right? So this x gets multiplied with W1 and with W2 because we are doing here this matrix product, okay? So what we are getting out here is then a C times 1-dimensional vector. Okay, so the output of this is C times 1-dimensional. For every class, I'm getting a score. And then, of course, I can also add this bias term. For every class, I have this single bias term, so to say. So what we are getting out here is a C-dimensional vector. Okay, so this is a C-dimensional vector. And this is what we then plug in into the softmax. Okay, so this is the softmax function. Okay, so the C-dimensional vector gets, as we have defined here, gets transformed to another C-dimensional vector, which we can interpret as a probability distribution. And then it indicates the likelihood for every class here. So this is usually the notation which is used nowadays in all the, let's say also the modern neural network formulation. We usually don't do this per class individually, but we just have this matrix notation where we have here all the parameters which we have to learn for all these different classes. We have our input and we have here also a vector. Okay, so please become familiar with this matrix notation again, which we also use in linear regression a bit already. But here it's also on the different models, so to say. We have per class, combining them all together, and then having this multivariate extension of the sigmoid, the softmax. Okay, so this is a very compact representation of our LDA model. And again, to more or less like wrap this up, so what did we do? We defined our model first. We picked to be, we selected the categorical distribution for the prior, and we picked like our class conditional, which were these Gaussians, which have the shared covariance structure. And then we said we have to do our maximum likelihood estimate, which is rather easy to do. And we derived our sigma and we derived the different mu's. Okay. So now what you have to do for the inference is you first compute WCs and W0s, right? Just plug in these terms here, right? Because you already did the learning. Just compute these different C's, stack it together to a matrix, right? You get this big W matrix. Stack this together to a vector, you get this W0 vector, right? And then once you get a new sample arriving, you evaluate this function, you plug it, and this is a vectorized function, right? It's a vector. You plug this vector into the softmax function. What you get out is a probability vector, okay? Probability vector, and then you can take the class which has the highest probability. Okay, so this is the flow of this model. So one last term you should have heard about is often these terms here are called the Logits. Okay, so these are the Logits. These are the values before we applied the softmax, and then what we are getting out here then are the corresponding probabilities. Okay, so these are often called the Logits, and then afterwards we have our final probabilities. Okay, so this was one function or one approach how we can set up a generative model, but this is not the only one. I quickly want to talk about a second approach here. And as you can imagine, in this simple setting we just talked about, we don't have too much flexibility to change, right? We can only pick a prior and we can pick a class conditional, and the rest just follows, right? So what we have seen here is really it just follows by solving the maximum likelihood estimate and seeing what is the probability for a class. So this was not like what we have really assumed. This just follows, and this is how we got our prediction. So the only change we can do, so to say, is that we can pick a different class conditional. And here we talk about a second variant, which is the so-called naive Bayes variant. So a very famous classifier, a naive Bayes classifier, is essentially doing this here. And what is the assumption of the naive Bayes classifier? So the only difference, more or less, is what we assume here for our class conditionals. And I directly want to jump to this here because it's much easier to talk about. So here we assume that, as before, we have a specific mean per class. Fine, you know how to derive it, right? Just compute the empirical mean. But we also have a specific or an individual covariance per class. So before I said we shouldn't do this, right? We shouldn't use a specific covariance matrix per class, because then we have too many parameters, right? Because we would have C times D parameters, right? This would quickly blow up. So why do we do this here? Because we put a specific assumption on this covariance matrix. We assume it's only a diagonal covariance matrix. Okay, so your sigma might look like this here, right? So 1, 2, and 5 or whatever. And here it's all zeros, right? 0, 0, 0, 0, 0, 0. Okay, so here we have only terms on the diagonal and 0 on the off diagonals. So this is the assumption we pose here. So from a technical side, of course, this simply means then that the number of parameters is we have C many D means, right? For every class we have to compute a mean, which is D-dimensional. And then for every class I compute a diagonal covariance matrix, which also just needs D many parameters, right? Instead of having D times D, we just need D many diagonal terms. So overall, the number of parameters is only C times D. So again, very compact. Okay. So that's the assumption of naive Bayes, diagonal covariance structure. And what does this diagonal covariance structure mean? So why is it called naive Bayes as well? Because this diagonal covariance structure simply means that we assume that the different dimensions, the different features in our data are independent, or that we be more specific, they're actually conditional independent given the class. Okay, so why, or what does this mean? So if you look at this class conditional, right, and let's say we have a multivariate case, right, we have d-dimensional input data x, and again it's conditioned already on the class C, right, because we have this process firstly sampling C, and then given C we sample x, right? So this is our class conditional, and the naive Bayes assumes that it can be factorized in such a way. Right, it can be factorized that every dimension acts on its own, right? We have a distribution over dimension 1, a distribution over dimension 2, a distribution over dimension 3, and the result is simply the product of these. Okay, so we have an independent assumption on the features here. Okay, and this corresponds to a diagonal covariance structure, meaning here, right, the features itself are not correlated. Okay, they are not dependent, but let's be specific and carefully, they are conditional independent. Knowing the class label C, we can do this factorization. It does not mean that the features itself are independent, right? If you would ignore this here, right, if you would just look at P of x1, x2, right, it might not be equal to px1 times px2. Right? So this is what we don't assume. We don't assume this. Just be careful. Careful. I mean, it might hold, but it might also not hold. Right? But please be careful. This might not be equal, right? It might be unequal. But what is true is that given the class, we assume this factorization. So this is conditional independent given the class. So that's the assumption of the naive Bayes classifier. We don't have correlation, so to say, between these features. And this is the only difference to the LDA, where we assume that the features can be correlated, but they have to share. They have to share their covariance matrix. So what does this mean graphically? Graphically, it means the following. So in the naive Bayes setting, right, and it's called naive because we assume the features are not correlated. In naive Bayes, it might look like this here, right? We have a specific mean per class. So let's say it is class red mean, and it has a specific covariance structure, which can look like this. And then we have another class blue, and it has a specific covariance structure, which might look like this. And then we have a specific mean for the third class, and we have a specific covariance structure. Okay. So what you see is that all of these classes, they have different covariances, right? One is like tilted in this direction, one is more like a circle, one is more like stretched around this direction. Important, however, is that the dimensions, the features are conditional independent, right? So these here are, so to say, axis aligned, right? It's always like this, or it's a circle, right? So this is a naive Bayes, while the LDA approach can capture correlations in the features. What this means is for class red, I can have something like this here, can be tilted, right? You see that we have here this correlation, right? If this feature is getting larger, the other feature is getting smaller, right? We have like this correlation in the features, right? Here it's tilted, which we don't have here, right? It's always like axis aligned. But important, if we have another class, it has the same covariance structure. Okay? So all classes, I don't know, let's draw it here, right? All classes have the same covariance structure. So the sigma is shared. So they have here all the same shared correlation structure, just the mean is different, but it can be tilted. In naive Bayes, we have always this axis uncorrelated covariance matrix, but it can be different per class, right? You see that these are really two different aspects, right? And both somehow allow parameter efficiency, because here we only have once a D times D matrix, and here we have C times a D-dimensional covariance information, so to say. Okay, so in both cases, the number of parameters is rather small, and so it's okayish to learn this structure. Okay, so this is like the graphical illustration of these two different approaches, and this is what you should really remember, right? If you think about, again, this generative perspective, right? The generative perspective means you first decide on a class, and then once you know which class you are in, then you can generate a sample. And this last part of the generative process, these class conditionals, is the only difference, right? And you see that in the LDA, you could generate data which looks like this here, right? But in the naive Bayes, you can generate data which looks like this here. Okay? So that's the only difference. And the rest, indeed, follows to be more or less the same, right? We can do now the same analysis as before. We can look at what happens, for example, if we have two classes. How does the decision boundary look like? Okay. So first of all, what we derived here, let me quickly scroll back at this part. No, here actually at this part. What we derived here, this probability for class 1 is like a sigmoid depending on this shortcut A, right? This is agnostic to the model choice, right? You see that we didn't assume anything about Gaussians or whatever, right? So this is always the solution. It's always like sigmoid of this A term, of this log ratio term. Okay, and so we can also apply this for the naive Bayes analysis, right? So we now want to see again, how does this A look like, right? Because we know if A equals to 0, this is the decision boundary. If A is larger than 0, it's class 1. If A is smaller than 0, then it's the other class, okay? So this also holds for naive Bayes. So we want to look at this A in the following. Let me scroll back and let's see how this looks like for naive Bayes. So here's again this A, right? The log of these ratios between the two classes. And if we make this equal to 0, as you know, right, then we are on the decision boundary. We are in the case where exactly between two classes. And now we plug in our assumption. Only now we plug it in. So here we plug in now our new Gaussian, so to say, right, where we have a different covariance matrix per class. And this is what you see here. So here you have like covariance matrix 0, covariance matrix 1. You have the two different means here. Here again, one covariance and the other covariance. So this is again just a nice homework. Plug in these distributions. So here the Gaussian, here the categorical one, which is not really important actually. As usual, here the Gaussian and here the categorical one. Okay. So by the way, for the categorical, we assumed here these pi terms, pi 1 and pi 0, which we called before actually theta, right? So here, these are the class proportions. So the distribution on y. So relating to the p of y. Okay, good. So the only difference, as said, is that we plug in now here different Gaussians. We plug in Gaussians where they have a separate diagonal covariance matrix. And again, we can simplify this, right? We can group together different terms, right? You see here we have quadratic terms, x and x is here, and here's only a single x. This has no x, this has no x, this has no x, right? So at the end of the day, we get here like this quadratic term, which comes from here. We have a linear term, which comes from here, and then we have a constant term, which does not depend on x, which comes from here. Here are just the shortcuts, okay? So this is really just deriving this or simplifying and regrouping. And now you see the big difference. The difference to before was that in the previous case, we only had this linear function, right? So the decision boundary was this hyperplane, was this linear function. Now we see that the decision boundary also contains quadratic terms. And this is a big difference to the Lda approach. Indeed, the naive Bayes classifier allows us to find quadratic decision boundaries. So here's the example which we can get, for example, from a naive Bayes. Again, you see from before, right? We have here different covariance matrices like this and this, but they are all like assuming uncorrelated features, right? So no tilt, so to say. And then you see if you draw this, that the decision boundary here would be linear, for example, because these two have the same structure. And this would essentially mean similar to the Lda, right? Once two distributions have the same covariance structure, the decision between these two would be a linear one. But you see that these two, for example, have a different covariance structure. And then we are getting this quadratic term here as well, right? We are getting overall like potentially quadratic decision boundaries, right? So here and here and then here, okay? So naive Bayes might result in quadratic decision boundaries, or it's very likely actually, and in contrast to Lda, can only lead to linear decision boundaries. So what we also nicely see in this equation is, why does Lda lead to linear decision boundaries again? So if we look at this simplification and we look at the quadratic term here, right, which depends on this W2 matrix. What is this W2 matrix? It's one covariance matrix minus the other one. And of course, if these two are similar, identical, like in Lda, right? They're assumed identical, they are shared. Of course, this term becomes 0, this term disappears, and what is left is a linear decision boundary. And this is why this Lda has this nice property of having linear decision boundaries, because this term simply disappears. Okay, so you see these two models are really somewhat different in their expressiveness and flexibility. As I said already, naive Bayes allows these different covariance structures, however uncorrelated, and then it leads to quadratic ones, which might be nice. On the other hand, Lda allows this tilt. So there's no clear answer, which might be more powerful, which might be better for classification. It really depends how your data looks like. As I said already, in this model, we have to assume these distributions, and if your data of course has like distributions, or the data is distributed like this, for example, right? Let's say class blue has some samples which are arranged like this, then of course naive Bayes would not be a good idea, but Lda could be better, right? On the other hand, if your data really follows like these three distributions, then of course an Lda would not be good, because it has to force that this distribution, for example, also has to look like this, which might not be a good choice. So it really depends how your data actually looks like, how your data behaves, which of these two models is the better one. However, The naive Bayes, I would say, is a more frequently used one for one very specific reason, because it has lots of flexibility in modeling your data for one specific reason, because once we assume this independence between the features, and that was the core idea, that's why it's called naive, right? With features here are assumed conditional independent, right? So here we have this product over the different dimensions. It means essentially that we only have to find univariate distributions, right? Recall, this is a d-dimensional distribution, right? So this is like a d-dimensional vector space. Here, however, this is always univariate one-dimensional distributions. And why is this a big advantage? Because univariate distributions, we have many and we have lots of flexibility to also model various kinds of data. So for example, we can have data which looks like this, right? We have like a mixed heterogeneous continuous setting. So let's say we have like, we measure attributes of people. One is the age. One is like the study program, CS, for example. One is the hair color, I don't know, black. One is the grade in the machine learning lecture, 1.3, for example, right? So this could be your data, and this can be very nicely modeled with a naive Bayes. Because what do we need? We have to find these univariate distributions over X, right? And we can do this now essentially per feature, right? These are the univariate functions, and we can just pick the distributions according to the domain this data has. What I mean with this is the following. So age, for example, this apparently is a distribution over the, let's say, positive numbers, right? From 0 to infinity. So we can pick here, for example, some of like a truncated Gaussian, right? Which only models the positive part, okay? Or we might even have like here categorical distribution, right? Like your study program. It could be computer science, it could be biology, it could be something else, right? So for example, a discrete domain. And we could then use for the second feature categorical distribution, right? The third one, again, categorical distribution. The grade might be again some numerical, but it might not go to infinity, but it's just between 1 and 5, for example, right? And since these are only one-dimensional distributions, for all of these, we have usually available some default distribution, Gaussian, categorical, exponential, and so on and so forth, okay? And we can just take all these individual univariate distributions and we can multiply them, and then we get our prediction. So this is a big advantage of naive Bayes. It allows you to flexibly handle heterogeneous data, and this is why it's also so often used, because it can really handle this mixed data types which you often have in practice. So for LDA, it's not so easy, right? For LDA, it's not so easy because you have to then find, for example, a joint distribution over all these 4 attributes at the same time. So you have to find one distribution which handles categorical and numerical features at the same time, which is usually tricky, okay? So this is the strong advantage of naive Bayes. You have only to pick univariate distributions, and then you can do this. Okay, so this is then the end essentially of this first part of the probabilistic classifiers. So again, to wrap up, what we had is this generative point of view. We had this view that we have this model which starts from y, and then given the y, known the y, we can sample in x. Okay, this top-down approach from y to x. We had to pick then the choices of the distributions one more time, the prior and the class conditional, which could be, for example, the naive Bayes way or the LDA way. And then we have seen that we can just find the prediction for our classes by reformulating, by applying, so to say, Bayes rule, right? We can evaluate what class has the highest probability by, in the general case, doing this multi-class discriminant case. We have a weight matrix W times X plus an offset. We plug it into our sigmoid, onto our softmax function. We get out a probability vector, and then from this probability vector, we can see which class has which probability, and we can pick the one which has the highest probability. So that was the core idea of these generative models. And as said, this allows us to capture already a wide variety of scenarios, specifically in the naive Bayes setting. Okay, so with this, I guess we can take a short break here, and after the break we will continue with an alternative view on this problem where we don't use a generative model, but we use a so-called discriminative model. But before we start on that, as said, let's take a short break.